Okay, here we go. Hey, I just wanted to, hopefully you guys are all pretty smart at this, but just in case, I wanted to show you what it looks like to attach homework. So this is on Teams. I'm a student of Mr. Calanella's class, just so I can show you this. So if you click on his, mine looks the same at the top here, where you click where it says assignments. You click into, excuse me, one of your specific assignments. Let's just say I'm doing this one right here. And if you want to, when you need to attach your work and stuff, it's right here at the bottom, right here where it says add work. If I click on that right there, up pops a screen. Remember, we want you to take a picture of something. So where it says upload from your device right here, you simply click that. You got to navigate. Here are all my pictures. I'm going to send Mr. Calanella a horse's butt. So you click on the pictures, plural, that you need to attach. You attach them. Once that's done, you click done. And then on the upper right here, it says turn in right here. Click that button. So that's the process. And no, I will not literally send Mr. Calanella a picture of a horse's butt, although I am tempted to. I'll be a nice person and not do that. Okay, that's how that's done. All right, let's go over homework. Let me share the screen. We'll get started here. There we go. All right, so the homework was 6.2. Any specific questions on 6.2? Nothing? Okay, then just make sure that you send me a chat or something like that if you're too afraid to ask in public. Here we go. So let's see, it was 1 through 8 all. So most of these were multiple parts. So on number 1, it says it's an A to B part, so it says write the inverse, the contrapositive and then the inverse. So the contrapositive would be if 4n does not equal 68, then n does not equal 17. And the inverse of that would be if n does not equal 17, then 4n does not equal 68. Number 2, contrapositive would be if this is not blue, then those are not red and white. And the inverse would be if those are not red and white, then this is not blue. Number 3, let's see, the contrapositive would be if x plus 1 is odd, right? Then x is even. This is the first more challenging one because you can't just put the word not even. Well, if you're not even, then you're odd. And then the inverse would be if x is even, then x plus 1 is odd. All right, number 4, the contrapositive would be if Abby is well, right, then she is here. And the inverse would be if Abby is here, then she is well. That was 1 through 4. All right, this table thing here, I'm just going to call off the true-false column. That's the last column. So what's true and false? And you were asked to write the statement, the contrapositive, the converse, and the inverse. So we're going to go statement, contrapositive, converse, inverse. So for number 5, it would be true, true, false, false. That's the statement, contrapositive, converse, inverse. If you have to rewind the video in order to hear that. Number 6, once again, statement, converse, converse. Boy, did I mess it up. Statement, contrapositive, converse, inverse. So that would be true, true, false, false. Number 7, false, false, true, true. And number 8, everything's true. True, 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 true. All right, so that was 1 through 8. And then we had 11 and 12. 11 and 12 have an A, B, C, or D. You're asked to write the statement and then determine if you, or to see if you can make any conclusion based on this. So you're supposed to write it in an if-then statement. So for part A, 11A, if you are a senator, then you are at least 30 years old would be the statement. And statement number A is Jose is 48 years old. Well, if he's 48 years old, we don't know if he could be a senator, but he also might not be. So no conclusion on that. B says Rebecca is a senator, therefore she must be at least 30 years old. She would be in the circle of senator and 30 years old. Constance is not a senator. Well, doesn't tell us how old she is. She might not be a senator because she's not 30, or she might not be a senator because she didn't want to be a senator. So no conclusion on C. And D is 29 years old, or this person's 29 years old, so therefore he can't be a senator. So we can't conclude that. So I'll say that one more time. A is no conclusion. B is she is at least 30 years old. C is no conclusion. And D is he is not a senator. All right, 12, the statement would be, if you are a math teacher, then you assign hours of homework. Hey, that's true, right? Part A, Bridget is a math teacher, so therefore she assigns hours of homework. Part B, August assigns hours of homework. No conclusion, because you could be a history teacher and also assign hours of homework, or a biology teacher, chemistry teacher, that sort of thing. Part C assigns no homework. If you assign no homework, you're not a math teacher, right? That would be the conclusion. And part D is not a math teacher. Well, if you're not a math teacher, you still could assign hours of homework, so we can arrive at no conclusion for that. Okay, and that was it. If you have any specific questions on that and you weren't here, you're watching this as a video, please send me a chat or an email. Okay. All right, quiz tomorrow. The quiz tomorrow will be as follows. You will need to be able to create a converse, an inverse, and a contrapositive of a statement, and figure out whether the statements are true or false. That's what the quiz will be on tomorrow. The quiz will pop up at the same time, about 7 a.m. We're not going to take class time to do the quiz. I'll just say, hey, you got the quiz today. It'll be a 10-minute quiz on your own. Please don't exchange ideas. You know, be a good, ethical, moral citizens and students, and take your assessments as you would normally in class. So I'll just ask you to do both a homework assignment and a quiz tomorrow. Okay. All right, and they will both appear as assignments: the quiz and the homework. Same thing. You get the choice of whether you want to, for quizzes and tests, you get the choice whether you want to print it off, fill it out, and then take a picture of it, or you can just pull out a sheet of paper and you can write the answers down. There's no work on the ones that I'll give you, but typically there's work involved. So when there is work involved, I need to see the work. So don't just put answers. The quiz, there won't be any work because you're just making statements. Okay. Here we go. Tonight's homework. This is kind of cool. I can have something to drink while I teach. Diet Pepsi. Okay, everybody got this copy down? Wes, you good? Okay. Jenna, good? Okay, here we go. Woo, today is challenging. It's just proofs. It's a whole day about proofs. All right. Turns out we've been doing proofs since chapter 2. It turns out we've been doing something called direct proofs. We have forms of proofs, or how you actually write the proofs. We've been writing 2-column proofs. We also have paragraph proofs. Those are the forms of proofs, but there's types of proofs as well too. So the types of proofs that we see in high school are what are called direct proofs and indirect proofs. So a direct proof is what we've been doing in the past. Today we're going to learn a new technique called an indirect proof. It's also called proof by contradiction. In fact, most books call it both. Our book chooses not to use proof by contradiction, but you're going to see this. But all books also call them indirect proofs. Like I said, today's going to be a challenging class. All right, here we go. First thing off, write this down. A contradiction. A contradiction is a combination of statements, plural. It's got to be 2 or more statements, ideas or features of a situation that are opposed to one another. In other words, you have 2 or more things that don't agree with each other, right? Two opposing ideas, so to speak. I mean, here's an example. Mr. C likes to eat healthy, and Mr. C only eats Oreos. So even though I like Oreos, right, if I were to only eat Oreos, I think we can all agree that that would not be a healthy diet. And these 2 statements, that Mr. C likes to eat healthy and Mr. C only eats Oreos, contradict each other. Okay, so That's an example of a contradiction, a combination of statements, ideas, or features of a situation that are opposed to one another. Everybody good? You got it copied down? Okay. All right, so up till now, this is kind of what I said before. We've been doing proofs. We've been doing lots of proofs. We see proofs every day. Here's a statement. If you have two even numbers, their sum is even, right? If I give you two even numbers, ask you to add them together, supposedly that their sum is even. So if I were to ask you to prove that statement, right? Well, we would do something called a direct proof. And a direct proof is I directly prove that their sum is even, right? I could also prove the contrapositive, as we found out yesterday. So if the sum of two numbers is not even, then I do not have two even numbers. I could prove the contrapositive as well. But I would still have to directly prove that contrapositive statement. So it turns out there's another way of doing that. That's the method that we'll learn today, and that's called an indirect proof. An indirect proof, or a proof by contradiction, is as follows. We're going to assume the opposite is true. In other words, it says if you have two even numbers, then I'm going to claim that their sum is odd. So I'm going to make an assumption here that contradicts what we're trying to prove. So I'm going to assume that the opposite is true, that their sum is odd, that the sum of two even numbers is odd, and somehow that's going to lead me to a contradiction. And as soon as I find that contradiction, then I know that the opposite must be true. In other words, two numbers can either only be both even or both odd, or one or the other, right? So if I assume that the sum of two even numbers is odd, all right, and it ends up being not true, then the only thing I can conclude, because there's only one option, either the sum is either odd or the sum is even, right? Hopefully that made sense. Okay, so write this down, please. This is the actual definition. An indirect proof. This is a proof where you temporarily assume that the desired conclusion is not true. Hey, prove that these two parts are congruent. So I'm going to assume that they are not congruent temporarily. What happens is you then do the proof, and this will lead to a contradiction. Well, clearly, because if it's not true, then you're going to run into problems. So you assume temporarily that the desired conclusion is not true. In other words, you reverse it. You do a proof, and eventually that's going to lead to a contradiction. As soon as you see the contradiction, well, then you can absolutely conclude that the proof has got to be true, because it's the only possibility. This is also called a proof by contradiction. So for some of you, you might immediately grasp this concept. Others of you are like, I don't get any. I'm writing down words. It doesn't make any sense to me. Show me an example. That's what we'll do today. So I will show you an example of multiple examples of proof by contradictions. Good? Everybody good? Okay. So I noticed that no one is live today, so I'm going to ask you to pause the video and write down all three of these steps. Okay. Step number one is you assume temporarily that the conclusion is not true. Step two is you're going to reason logically. In other words, you're going to do a proof. You're going to continue the steps until you get to a contradiction of a known fact. Right? You get to, I don't know, you assume something, and all of a sudden you figure out that squares have 5 sides. Well, that contradicts the fact that you know that a square is a quadrilateral. You're going to continue this logical process of writing your proof until you arrive at a contradiction. I really got to show you an example for this to make sense. So as soon as you arrive at that contradiction, step number 3, you point out that the temporary assumption must be false because you arrived at a contradiction, right? Therefore, the conclusion must be true. All right, so do need you to pause the video, write down these steps in your book of truth. This is how you do an indirect proof. And I would also recommend that you choose one of the 3 proofs that we do today as examples and write it down. I'll show you the one that I would write down as an example of a proof by contradiction. This is an example I like to give to everyone. Let's just say, and I usually do this in class, let's just say that I'm wearing pants that only have 2 pockets. There's just 2 pockets. and I'm going to say there's a left one and a right pocket. I'm going to say there's $1 in one of my pockets. And so here's an example of a proof by contradiction. Prove that there is $1 in my left pocket. So a proof by contradiction would be something like, well, assume the opposite. Assume that the dollar isn't in my left pocket, assume it's in my right pocket. So I assume temporarily that the dollar is in my right pocket. And then what I do is I empty my right pocket. I show you that there is no dollar there. Well, I just assumed that the dollar was in my right pocket. So since I showed you, logically, I'm showing you what's in my right pocket now. There's no dollar there. Then the only other assumption that you can make is that it is in my left pocket. Okay, that's a proof by contradiction. We temporarily assume, so once again, I'll say this again. I only have two pockets. I have $1 in one of my pockets. I want to prove that the dollar is in my left pocket. So I temporarily assume, proof by contradiction, I temporarily assume that the dollar is in my right pocket. Then I show you what's in my right pocket. There's nothing there. Therefore, my assumption was false. There's a contradiction there. If it's in my right pocket, there should have been $1 there. Therefore, I don't even have to look in my left pocket. We can conclude that there's $1 there. Now, why would you do a proof by contradiction? Sometimes a proof by contradiction is easier to do than a direct proof. And later on in the chapter, or in the book, I should say, we will do a proof by contradiction a couple times, and you'll see why it's very convenient. Generally, when you try to do a direct proof, you run into a problem, you can't get anywhere, you don't make any progress. You try a proof by contradiction, you find out it's pretty easy. I'm going to show you the first example. I'm going to show you deals with even numbers. So first off, this is a tangent here, going off on a tangent. We're talking about even numbers. So what is an even number? An even number, well, here an example, 2, 4, 6, 8, 10, so forth and so on. 0 is also an even number. So what is an even number? Well, that's a number that's divisible by 2, right? Mathematicians define even numbers not through division, but through multiplication. We say take the number 2 and multiply it by an integer, positive, negative, it doesn't matter, just an integer. And the result of this multiplication results in an even number. So let's say k is 3, 2 times 3 is 6, 6 is an even number. 2 times 10, 2 times 10 is 20, 20 is an even number. So k is just an integer. It can be positive or negative, right? 2 times negative 7 is negative 14, negative 14 is an even number, okay? So mathematicians don't define even numbers as division, we define it as multiplication. So 2 times any number k, where k is an integer. 0, 2 times 0, 0, right? So 0 is an even number. Okay, so I'm going to use that as an example of how to do a proof by contradiction. So here's my proof by contradiction. It says m and n are even. And I want to prove that m plus n is even. Okay, so how will we do that? Well, we could do this directly, but I'm going to show you an indirect proof. So indirect proofs start off exactly the way direct proof starts off, with the given. The second step of an indirect proof is where it changes. We're going to make a temporary assumption that negates or changes the proof part. So instead of proving that the sum of m and n is even, I'm going to temporarily assume that the sum of m and n is odd. Okay, and this is called, and then the reason for this is we cite proof by contradiction. So remember, proof by contradiction, you temporarily assume that what you're trying to prove is false. You negate it, okay? This works really well when there's only a binary choice. Binary means there's only two choices. Hey, the dollar is either in my left pocket or my right pocket. Hey, the sum of m and n is either even or odd. There's no other choice. There's no other choice, okay? All right, so that's my temporary assumption. Now what I'm going to do is I'm going to continue the logic until I get to a contradiction. The contradiction of the dollar in the pocket was that when I showed you what's in my right pocket, there's no dollar there, so therefore my assumption was false. So I need to somehow prove that, that this arrives at a contradiction. All right, so here's how I would do it. Well, we know from the previous slide I showed you that you can define any even number as 2 times k, where k is an integer. So I'm going to define m as 2 times k. N is a different even number, right? And we're going to define it as 2 times L, okay? So remember, K and L wouldn't, if they were both K, they would be literally the same even number. So I'm going to assign a k for the first even number, L for the second one. 2 times whatever k is the even number. 2 times L, whatever L is, that's the even number. Okay? K and L have to be integers, though. All right, and this is just the definition of an even number. Okay? It says we're supposed to add these two together, and it's even. So we're going to add these two together. M plus N, therefore, would be 2K, because I just defined it right here, plus 2L. What's that? That's just plain old addition. Okay? M plus N is equal to 2K plus 2L. Okay? If you look at the left side, or sorry, the right side of this equation right here, we have 2 times K plus 2 times L. We could do a little bit of algebra here and do some factoring. If I factor a 2 out of both of these terms, 2K and 2L, well, I could write it like that, right? All I'm doing is a distributive property in reverse. That's called factoring, okay? Okay, well, that's just factoring. What's K plus L? Well, any integer, K is an integer, L is an integer, any integer plus another integer, can you ever get a fraction out of that or a decimal? If I take an integer and I add another integer, can you ever get a fraction or a decimal? And the answer is no. So K plus L must give you an integer. I don't know what that integer is. I'll just call it J, okay? So K plus L, an integer plus 1 plus 2 is 3. 1 plus negative 4 is negative 3. Each time I'm getting an integer. So I don't know what the integer is, but I do know that K plus L is another integer. We'll call it J. So now I just showed you that M plus N is 2 times J. Wait a minute. 2 times J is 2 times an integer. So this part right here, well, that's, by the way, what's the sum of 2 integers in an integer? So 2 times J, well, that's the definition of an even number, right? 2 times an integer. So I just showed you that M plus N is actually an even number, and that contradicts the fact that we were supposed to show that M plus N is odd. Okay, so that contradicted our initial assumption. So our assumption was that M plus N was odd. Well, there's only one, since we just arrived at a contradiction, there's only one other possibility, and that's that, well, M plus N must be even. Okay, so even numbers, 2 times K. Okay, that was my contradiction. So there's an example of proof by contradiction. All right, challenging? Oh, heck yes, it's challenging. So therefore, we better do a different one. So here's a nice geometry one. Previous one was an algebra one. So here's a nice geometry proof by contradiction. So it says I got a trapezoid, PQRS. The bases are SR and PQ. Somehow we're supposed to prove that PQ is not equal to SR. In other words, the measurement of the two bases are not equal. All right. Once again, proof by contradiction works great when there's a binary choice. Think about it. There's only 2 possibilities. Either PQ is equal to SR or it's not equal. There's no third choice. So this is why when proof by contradiction works really well, when there's only 2 choices. Either they're equal or they're not equal. There's no other option. Okay? So we're going to prove this one by a proof by contradiction. So step number 1 is that you assume that the proof part is the opposite of what it says. So the opposite of PQ is not equal to SR is that PQ would be equal to SR. So that's our proof. That's our proof by contradiction. Is we start by assuming the opposite of the proof. So we're going to assume by contradiction that PQ equals SR. This is proof by contradiction. And then what's going to happen is we're going to do some logic here, and eventually we're going to find that our logic is faulty. So if PQ equals SR, and we continue until we get to something that's false, then therefore my assumption must be false. And since there's only one other option, if PQ does not equal SR, well then the only other option is they're not equal. All right, so let's see if we can arrive at a contradiction. Well, let's see. This says that PQ is equal. So if PQ equals SR, then, well, by the definition of congruence, then PQ must be congruent to SR. I mean, that's the definition of congruent. If PQ equals SR, then those 2 segments are congruent. Okay? It's trapezoid. So if it's a trapezoid, what do you know about SR and PQ? Well, by definition of a trapezoid, the 2 bases are parallel. So therefore, PQ and SR are parallel. Okay? So we get that specifically by definition of a trapezoid. By definition of a trapezoid. Okay. Chris, mute. Thank you. I have no idea what that was. That was horrible. Okay. PQRS is a parallel. What? PQRS is a parallelogram? I thought it was supposed to be a trapezoid. Why can I conclude that PQRS is a parallelogram? Look at the previous two statements. I just showed you that PQ and SR were both congruent and parallel. And if we think about to the previous chapter on quadrilaterals, whenever you have two sides of a quadrilateral that are both congruent and parallel, this is theorem 5.5, then you conclude that it's a parallelogram. Once again, if you have a quadrilateral, we got a quadrilateral, we got a trapezoid, right? If two sides are both congruent and parallel, then it's got to be a parallel. Can you see the contradiction here? We know that PQRS is a trapezoid, yet we just proved that it's a parallelogram. That can't happen, right? Why did that happen? One, because we were doing a proof by contradiction. We made an assumption about PQ and SR that was faulty. PQ cannot equal SR. And this is why we arrived at that contradiction, because we assumed that they were equal. And since they were equal, we finally, using straight good logic, we figured out that PQRS is a parallelogram. PQRS is not a parallelogram, it's a trapezoid. So proof by contradiction, you assume that the proof part is not true. That leads to a contradiction. Therefore, the only thing you can conclude is that since that is a contradiction, that it must be false. PQ cannot equal SR. By the way, that's what we were trying to prove. That's why this one works. What was the contradiction? The contradiction is that it contradicts that the given was a trapezoid, not a parallelogram. Proof by contradiction, once you get the hang of it, are pretty nifty, but oh, when you first start, they are challenging. I said we're going to do 3 proofs. We just did 2 proofs. All right, QED. So practice writing proof by contradiction. We're just going to do another one, and that's going to be our practice. Okay, so let's see. This one is an easier of the 3 that we've done so far. So it says you're given that PQRS is a rectangle this time, and the perimeter of PQRS is 16, and that one of the sides, SR, the top one right here, is equal to 6. Somehow we're supposed to prove that SP is not equal to 3? Just think about that. Trying to prove that would be really challenging. I know the perimeter is 16. I know one of the sides is 6. This will be a challenging thing to do directly, but indirectly, it's pretty simple. Watch how simple this is done indirectly. All right, so an indirect proof is you start off with the given. The given is that I got a rectangle, the perimeter is 16, and SR is equal to 6. Proof by contradiction takes the proof and changes it. So instead of SP not equal to 3, we assume the opposite. So we're going to assume that SP equals 3. So assume by contradiction that SP equals 3. I just take the proof and I write the opposite of it. All right, this is proof by contradiction. We're going to do some logic here, and we're going to find out that this cannot happen. We arrive at some contradiction. Okay, so what contradiction could we arrive at? Well, let's see. What are we given? We're given that's a rectangle in the perimeter. So I could write a quick equation for the perimeter. So the perimeter of PQRS will be equal to the 4 sides added together. Right? That's pretty simple. Right? 4 sides added together. That's the definition of perimeter. Now I'm going to plug in what I know. Well, I know that SR is 6. Well, SR is 6. Well, I know it's a rectangle. So let's see. We got all the things for rectangles. Opposite sides are congruent. So if SR is equal to 6, I know that PQ would be equal to 6. From the given, we're given that that's all we know. And then from the contradiction, we are going to assume that SP is equal to 3. So if SP is equal to 3, since it's a rectangle, then RQ is equal to 3. So once again, where did I get all these numbers from? Well, we're given that it's 16. Our assumption is, or SR is equal to 6, so therefore PQ is equal to 6. And we're assuming by contradiction that SP equals 3. Okay, so if SP equals 3, then so does RQ. That's where I got all my numbers from. Well, let's add this up. 6 plus 3. Oh, by the way, that's just substitution, opposite sides are congruent. 6 plus 6 is 12, plus 3 is 15, plus 3 is 18. Oh, that's just addition or simplifying. Well, that's clearly not true. 16 does not equal 18. Remember, proof by contradiction, we make an assumption, we use logic, we get to a contradiction. Clearly, that's a contradiction. 16 equal to 18. As soon as you get to that contradiction, you are done. You can immediately assume that your assumption was false. So if my assumption was false, SP can't equal 3. I don't know what it equals something else, right? So therefore it cannot equal 3, and that contradicts our assumption. Okay? That's how proof by contradiction is done. Questions? Okay? Nope. I absolutely 100%. I usually have lots of questions on this homework. So it's just 1 through 5. Obviously, since it's a proof by contradiction class, questions 1 through 5 will be questions on proof by contradiction. Okay. If you have any questions about the homework, let me help you. Like I said, some people find this much more challenging than direct proofs. That's all I have for class today. Chris, you got any questions? Nothing? Okay. And I will conclude class. Here was your homework for those who didn't copy it down. Chris is here. The rest of you are watching this recording. Chris, your homework's due tomorrow. Everyone else, your homework is due tomorrow as well, or the day that you watch this class. So if you're watching the video, then your homework is due the day that you watch it. So Chris, you got until tomorrow. Everyone else that's watching a video of this, yours is due. Let's see, today is Thursday, so yours is due by midnight on Friday. And that's all I got for you. You guys have a wonderful day, and I will see you guys tomorrow. Oh, I just saw your explanation of what the noise was there for, Chris.